Okay, so I'm going to tell you about, we're going to continue on similar topic actually than what Alexandra was talking about. So we're going to have, I mean, here convexity will appear, and I think there are similarities between what I will discuss and what Alexandra was talking about, but okay. So the problem that I will tell you about is linear bandit. Okay, so this is a problem where we're going to develop much more interesting mirror map than we have been doing so far. So this is what I will do this hour, and then next hour, the last part of the course will be the chapter 5 on adaptivity. Okay, so what is the linear bandit problem? It's like this. Fix K, a convex body in Rn. This is a convex body. And what we're going to do is that we're going to play, you know, the type of sequential games that we have been playing so far, but instead of selecting point in the simplex, as we have been doing so far, we will select point in K. And what the adversary will do, the sequence of loss function, will be, just as it has been so far, a sequence of loss vectors in Rn also. Okay, so fix K in Rn. Now, at every time t, bigger than 1, the player selects xt in K, and the adversary selects lt, let's say, in Rn. And your loss is, just as we have been doing so far, the inner product between lt and xt. Okay, so it's kind of a huge generalization of what we have been doing so far, okay, for prediction with expert advice or multi-arm bandit. So the loss is the inner product lt.xt. Okay, so one small difference, say for instance for multi-arm bandit or prediction with expert advice, we're looking at K, which was the simplex, but really we were not actually playing xt, we were playing a point at random from this distribution. Okay, so I don't want to dwell on this. If K was a polytope, it might be more natural to play only the vertices of the polytope, but there are reductions between those two things. Okay, so we're just going to assume that we play in this continuous thing. If it was the full information problem, so what's called the full information problem is when LT is revealed at the end of the game, then it really makes no difference at all. But we're going to be talking about the bandit problem where only this thing is revealed. So for the bandit problem, there is a difference a priori between observing lt.xt or observing, you know, lt.at, where at would be constrained to be a vertex of K. But I don't want to dwell onto that. Okay, so again, we'll look at bandit feedback. Only observe the loss, your loss. Okay, and I just want to clarify, why is this a far-reaching generalization? There are many, for instance, combinatorial problems that can be cast like this. Imagine that you have some combinatorial optimization problem. I don't know, you have to choose a spanning tree in a graph, or you have to choose a certain path in a graph, an ST path in a graph. Then you can view K to be the convex hull of all of those things. And LT is just assigning a loss for every edge. So then, you know, if you select a path in your graph, you're just paying the sum of the losses on all the edges in the path that you selected. Okay? So one huge application of this is to revisit all of combinatorial optimization, you know, under the lens of online decision making with bandit feedback. Okay? But I want to focus on this more abstract version of the problem where we have a convex body and we can play actions in the convex body. Any question on this? I don't want to talk too much about applications, but I also want you to be properly motivated to spend an hour on this. So any question? Yeah?
Can the loss be noisy, for example?
Yeah. So again, you know, like making no assumption on the losses is much more general than assuming anything. So in particular, it's more general than assuming noise. Right? It covers noise. Like LT could be noisy. Doesn't matter. Okay. All right. Well, we know how to solve this problem. We're just going to apply mirror descent. Okay, but just as always, as we had the problem with multi-arm bandit, so we want to do mirror descent. But with what gradient? Okay, mirror descent. Question, what is GT? Okay, what is the gradient that we should be using? So you remember in multi-arm bandit, we had this very cute trick that you play an action at random, and you just reweight by the probability of playing that action, and you estimate a loss of 0 for all the other action, and that was unbiased, an unbiased estimator. And then we had this amazing variance calculation where everything cancels, and it was great. We were very happy. Now it's a much more tricky problem, right? Because again, let me just again draw this example of, say I have a graph like this, a grid. Okay, and my dimension n is the number of edges in this graph. And say k is a polytope of st paths. So I have to choose, let's say, an increasing path like that. Okay, so a path like this is a path, let's say a path p, that's an element of 0, 1 to the n. Right? It's just whether the edge is present or not. And let k be the convex hull of those p, of those paths. Okay, so what I'm choosing concretely in this problem is that I'm choosing a path in this thing. And I'm just observing the sum of the losses on the edges. Okay? But now I want to build a GT which is, an estimate of the loss on every edge individually. So that's, I have some disambiguation problem to do. I need to say, okay, I observed a loss of 10. Was it because there was a 1 here and a 9 here, or was it a 1 everywhere? You see the problem. But this is just, it's not such a big problem. It's just linear regression. Okay, it's just linear regression. The difficulty is that I have only 1 point. So the answer is 1 point linear regression. 1 point linear regression. So I'm going to write the formula for you, but if I tell you this, you can figure it out yourself. But again, what's going to be the problem? If you do linear regression with 1 point, what is the issue? There is a lot of variance, just as always. Now, in addition to the variance of having small probabilities, you have the variance of, basically a small eigenvalue. If you have some directions which are less explored than others, then you will have a problem. And again, mirror descent is going to come in to save the day. So mirror descent is going to exactly, you will have to have a mirror map that kind of matches the covariance of your sampling scheme. I will explain all of those things. Okay, so it's really all of the problems that we saw in multi-arm bandit, they are kind of magnified here, and it's a more tricky version of it. Okay, so what is this 1 point linear regression? So it's like this. So GT is going to be defined to be the following quantity. So let's say, I see what I'm doing here. Let me use the notation. Let me use the notation AT here. Okay. Because what am I going to do? So mirror descent will give me a point. This gives me a point xt in k. But to do linear regression, I will want to have randomness on top of it. So what I will have is what's called, here we have a new element, which is a sampling scheme. Sampling scheme. It's a map, let's say P from K to probability distribution over K. Okay, so what do I mean? I mean that it associates to a point a probability distribution over the entire convex body. So when we were in the simplex, there is a canonical sampling scheme, which is, if I have a point X, it's also a probability distribution, so I can also sample from that probability distribution. But for general convex bodies, I have more flexibility here. Okay, so let me add this ingredient of the sampling scheme, and I will denote the covariance of P of X. This is just the maybe cov of X. This is just the expectation when A is sampled from P of A minus mu transpose, where mu, let's say mu of X also. Mu of X is the expectation when A is sampled from P of A. Okay, so mu is the mean of my sampling scheme, and covariance is the covariance of my sampling scheme. Okay, and in fact, we are going to restrict to the following. In fact, yes? Yeah, please do. It's P of x, yes. Thank you, Joseph. Yeah. So yeah, let's slow down. So here, this is my convex body. K. Okay. I'm going to run mirror descent. Cha-cha-cha. I get here. I get to this point. This is my xt right now. I'm not going to play xt. Okay. This would be a deterministic move. We haven't really dwelled on this, but you cannot be deterministic. If you're predictable, then you know there is a bad sequence for you. So you can never be predictable. You have to be randomized. In multi-arm bandit, we were randomized very naturally because this k was just a simplex, so we were playing a probability distribution, and the randomization, I didn't really talk much about it. It's just sampling from this probability distribution. But now, the sampling is kind of more complicated, you know. If I want to play xt, so I only need to play xt in expectation. So what I'm going to assume, so we restrict to p such that mu of x is equal to x. Okay, so we restrict to sampling schemes which are unbiased. So I would like to play mirror descent at that point, but I need some randomness, so I'm going to randomize. Maybe, you know, I could sample from a small ball around this. Can imagine that sampling from a small ball is going to be a very terrible idea because, you know, I'm in high dimensions. Those things could have very, very tiny corners. So, you know, the ball could be exponentially small in the dimension. And then the smallest eigenvalue is going to be exponentially big. And we're going to have trouble with the variance. Okay, so we will need to be much smarter than doing small balls like this. And I'm going to explain all of this. But nevertheless, there is some sampling scheme that we can design. So now mirror descent tells me to play xt. And in fact, what I'm going to do is that I'm going to sample at from p of xt. This is the guy that I'm going to play. This at, it has mean xt, and it has a certain covariance. The covariance is cov of xt. Now, given all of these elements, I can build an unbiased estimator, which is the following thing. Let me just write the formula. It's the covariance at xt inverse applied to at minus xt. Maybe I want a bit more space. Times at transpose lt. Okay, this is a matrix. This is a vector. So this is a vector. This is a real number. So this is a vector. Okay, so this gt is an element of Rn. Okay, first sanity check. I'm predicting some vector of Rn. Moreover, in expectation, this is equal to Lt. In expectation over At sampled from xt. Why? Well, when I take the expectation with respect to At sampled from P of xt, you know, it's as if this is as if it was At minus xt because xt times this in expectation is 0. So I can assume that I have At minus xt here. So I have At minus xt transpose, which in expectation is the covariance of xt. So it cancels with the inverse covariance. Okay, so what I'm saying is the expectation when At is sampled from P of xt of gt, this is equal to Lt. Very good, very good. Yes, xt is going to be the point which is suggested by mirror descent. We're going to run mirror descent. It's in our background. It's this process which is deciding for us play that point. And now I'm saying I don't want to play deterministically. I'm going to randomize. So I play At. So in particular, notice that I know xt. That's kind of what my algorithm is going to tell me to play. I can calculate the covariance, the inverse covariance. And this is an observation that I made. So this is something I can actually compute. This is a fine thing to look at. Yeah, please.
What is the expectation of At minus xt, At transpose covariance? Because doesn't it then over the minus?
Right. I'm missing the minus xt. Let me add minus xt plus xt. And now so the term At minus xt is what I said. And the term plus xt, it's multiplied by this, which is 0 mean. So the expectation of it is 0. Okay, so now I can run mirror descent with gt. Mirror descent is telling me xt, And now instead of playing xt, I play at from p of xt. And this is my algorithm. Let's see what the regret is. Okay, the only thing we will have to calculate is the variance. Okay, so xt, so algorithm. Is going to be the following. Again, you remember xt plus 1 is going to be the projection on my set of constraints of the Bregman divergence between x and the unprojected point. What is the unprojected point? I take the gradient of phi at xt, that's the previous point that I had. I do a gradient step minus eta gt. Okay, and gt is this guy. And now, okay, this is a grad phi type term, so I need to map it back to the primal. And you remember the inverse map of the grad phi is the grad phi of the dual, so this is grad phi star of this thing. Okay, so that's what we spent the 3 hours of yesterday doing, so okay, hopefully this makes sense. This is mirror descent. Now, on top of it, I'm going to play at plus 1 is going to be sampled from p at xt plus 1. Okay, then observe lt plus 1 dot at plus 1, that's my loss, and build gt plus 1. Okay, and then I move to the next step. That's a fully specified algorithm which has 2 parameters, a mirror map phi and a sampling scheme p. And remember yesterday we solved multi-arm bandit by taking p to be the canonical sampling scheme for the simplex and phi to be the entropy or the Thalys entropy or the log barrier. These were the things. Okay, so what is the regret? Regret. Okay, so what's the definition? Let me be very clear. What is the regret that we control? The regret that we control is the sum for t equals 1 to capital T of gt inner product with xt minus x. That is the regret, which is kind of deterministically controlled by all the work we did yesterday. And what was it? This is bounded by 2 terms. So we get phi of, I called it y so far, so let me stay with y. This is bounded by phi of y minus phi of x1. This is the range of the mirror map, divided by eta, plus eta over 2, the sum for t equals 1 to capital T of what? Of the dual norm of gt at some omega t, which is close to xt, hopefully, dual squared. That's like true. That's just true. And that's what we proved yesterday. Now, this is, I called it regret. But what really is regret, That's like the regret controlled by the theorem. But really, what is our regret? Our regret is really the expectation of the sum for t equals 1 to capital T of lt dot at minus y. We didn't play xt. We played at. And we are not evaluated against gt. We're evaluated against lt. So that's the real thing that we care about. But now, for most of you, you see those 2 things are equal in expectation. Yes, please. Right, I put omega t, so this is what I was explaining yesterday. Really the theorem that we proved was the Bregman divergence of the Fenchel dual between blah and blah. And what I said is that by Taylor's theorem, this is equivalent to the Hessian applied to some omega t, which is in the range. Right. So I won't have time to explain this part in very much detail today, but it's very important and it's here. Okay, it's not exactly xt. You remember that's where yesterday we had the triple derivative of phi that appeared. We said if the triple derivative of phi is negative in the case of a separable mirror map, then this term I can replace omega t by xt. That's what I was explaining yesterday. Okay, maybe I just say that, and you guys are okay, or you want me to explain more? Yeah.
You're assuming y is non-random and opt?
Yes, opt is a fixed opt. This is a definition of regret for me. I want this term to be small for any y. Yeah. Yes, thank you. Yes, they are equal in expectation, yes. Yeah, so maybe let me put an expectation here also. I didn't want to put an expectation the first time I wrote this inequality because I wanted to emphasize that it's not an expectation inequality. This inequality was just true, like there is no randomness in it. The randomness only appears when I want to relate that guy to that guy. But the randomness is also going to appear now when I want to bound the variance. Just like yesterday for multi-arm bandit on the simplex, you remember, GT, it has like 1 over x squared in it. One of the x is cancelled by the local norm, and the other x is cancelled by the expectation. So we'll have the same kind of phenomenon here. Okay, any question on this equality? I mean, you just do it in 2 steps, right? You say first that the expectation of AT is xt. Okay, so this is equal to LT dot xt minus y. And now LT is equal in expectation over AT to GT. Okay, but you have to do it in 2 steps. There are 2 equalities here. If you do it once, you're in trouble. So you first replace AT by xt, and then you replace LT by GT. Point being that the regret of this algorithm is controlled by the range of the mirror map over eta plus eta times the variance term. So all we have to do is to control the variance term now. Okay. So what is the variance term? And this is going to be very interesting because we will have to match the geometry of the sampling of the distribution with the geometry of the mirror map. Okay, there will be some dualities there, which we're going to fully resolve. Okay, so the variance term, let me, again, not worry about the fact that this is an omega t instead of an xt. Okay, so let me take the expectation of the norm of gt at xt dual squared. Okay, so this is the expectation by definition of GT transpose Hessian phi at xt inverse because it's a dual GT. Okay, so this is, and maybe let me denote, let's introduce just a notation, sigma t. I will just say that this is a covariance at xt. Okay, sigma t is a covariance at xt, just to have a simplified notation. Okay, so what do I get? I get that this is equal to the expectation. I get my cost AT transpose LT squared. And then I get AT minus xt transpose sigma t inverse the Hessian of phi at xt inverse sigma t inverse AT minus xt. Okay, and I didn't talk about normalization yet, but the normalization. So assume that the loss is in minus 1, 1. Okay, this is my normalization. This is quite important. It changes the answer a lot. How do you normalize? You know, there are other ways to normalize. You could normalize by saying LT has to have losses between minus 1 and 1 for every coordinate. And that's quite different. But I don't want to talk about that. So this thing is smaller than 1. Right? The loss that you suffered. Now, what is this? And this is, of course, a positive quantity because, you know, it's a PSD matrix applied to some vector. So it's the quadratic form of this. Yeah, so let me, you know, just use the fact that, I don't know, A times A, this is a trace of A transpose. Maybe I could have picked other names than A and A, but right? I just use the cyclic property of the transpose. So what is this thing? This is the same thing as the trace of sigma t inverse Hessian phi inverse sigma t inverse applies to AT minus XT, AT minus XT transpose. Right? But now the point is in expectation when AT is sampled from P of XT, I get sigma t here. So one of the sigma t cancelled with the sigma t inverse. So this is equal in expectation to the trace of sigma t inverse times the Hessian phi at XT inverse. Okay, so now we're going to look like in the eyes this term and really try to understand it. What does it mean? So I just said the variance is bounded by this thing. Okay. So just to clarify, so conclusion, the corollary is if the trace of sigma t inverse Hessian phi at xt is bounded by some v for variance, then the regret is bounded by, so I get, the range, and I get t times v, so I get square root v t range. Okay, so I will need to estimate the range of my mirror map, and I get a variance term, and I get t for the number of times that the variance is being added up. So all I need is now to construct together a sampling scheme and a mirror map so that both the range and the variance are controlled. Okay, so let's look at this variance term. What happens again? So we expected, as soon as I wrote this thing, and I asked you, what's the problem with this estimator, and you told me the variance, we expected very early on that there is a problem when this inverse covariance goes to infinity. So when the covariance goes to 0. When does the covariance go to 0? The covariance goes to 0 when you're getting close to a corner. When you're getting close to a corner, if you want to be unbiased, you have less and less space to move. Okay, so the covariance is going to blow up. This is the same thing as for multi-arm bandit when we had the simplex. We had the same issue that when we started to be localized, when we wanted to play one action very much, we're messing with the exploration-exploitation trade-off. If there is one action we want to play a lot, and the other one are not played, then the probability of these other guys goes to 0, so 1 over this probability goes to infinity. Okay. So we have the same thing here with the inverse Hessian. Now what do we want? Now we want, but you see, sorry, there is an inverse here also. So when this goes to infinity, we will want this guy to go to 0. Meaning the Hessian should go to infinity. So what we would like is the Hessian of phi of x goes to infinity as x approaches the boundary of k. Okay, so we want the curvature to blow up as you get closer to the boundary of this object. Okay, so if we get the right matching exactly, then we will be saved and we'll have this thing to be controlled. Of course, there is a tension again, which is making phi to be bigger will also make the range bigger. So there is a subtle balance here. So let's see 2 ways to solve this, or one way at least. And in addition to, controlling v and range, there is also the problem of omega t versus xt. So this was up to omega t versus xt. which again I won't have time to explain. But this is also something that goes into the mix. Okay. So let me tell you one way to solve these problems, which is suboptimal but very beautiful and very insightful. So this is the Abernethy-Hazan-Rakhlin sampling scheme. So it solves everything at the same time by relating it to a well-known theory in optimization. So relation to inter-point methods. So I absolutely don't have time to tell you about inter-point methods and where they came from, etc. But so maybe some of the stuff that we'll say will look a bit out of nowhere, but it is all very well motivated. Okay? But still, ask me questions, and maybe by answering your questions, I can explain some of the magic. Okay. So the idea goes like this. The xt versus omega t problem is about whether the Hessian of phi at xt is of order of the Hessian of phi at omega t. Okay, and omega t is really a point which is basically on the segment between xt and xt plus 1. Okay, so this is a well-conditioning problem. And it is natural to look at functions which are well-conditioned like this on the size of a step which is controlled by the Hessian itself. Okay, so self-concordance, which is this thing that was defined in inter-point method, exactly tells you that the Hessian of phi at x is the same thing as the Hessian of phi at x plus h for any h which is small, for any h such that the norm of h, but the local norm of h, is smaller than, say, is smaller than 1. Okay, so these are functions. So eventually, remember, we want function whose Hessian blows up to infinity. Okay, so when you get closer here, the Hessian is very, very big. Okay, so a ball, when you get closer to here, like a ball, so this is a ball in the local norm at x. Because the Hessian is very big, this ball is very small. Okay, so as you get closer, the balls, they get smaller and smaller. And what this assumption is saying, what this definition says, that these are functions which remain well-conditioned on those balls. Okay, it's not totally obvious why this exists, etc., but yeah. Okay, but in particular, what do we get out of this? In particular, we get that this type of ball is included in the body. Okay, so in particular, for a self-concordant barrier. So what is a self-concordant barrier? It's a function which verifies this and which blows up to infinity at the boundary. Okay, so a barrier function is such that phi of x goes to infinity as x goes to the boundary of k. Okay, so in particular for a self-concordant barrier, what do we get? We get that the set of x plus h with the norm of h smaller than at x smaller than 1 is included in k. Because the Hessian is finite, and the Hessian is only finite inside the body. Okay, so this is called the Deccan Ellipsoid, this thing. Why does this matter a lot for us? Remember, what do we want? We want to match the covariance of the sampling scheme with the Hessian. But if I have if I have an ellipse like this, you know, the covariance is given by the by the quadratic form which gives you this ellipse. So the covariance of sampling from this ellipse is exactly going to be the inverse Hessian. Okay? So I'm going to do this calculation for you. But the point is, this thing is included in K, so I can sample from it. If I sample from this, I'm unbiased, and my covariance is exactly going to be the inverse Hessian, up to a multiplicative factor which depends on the dimension, which in turn will allow me to control this. Okay, so let me do this calculation for you. But first, did that make sense?
So maybe you did also the Hessian to work, like all eigenvalues.
Phi is convex. So I think, and K is a convex body, it's a compact set. So
it implies that all eigenvalues of the Hessian.
yes. Oh, I see. You're saying, yeah, it needs to be, yes. Yeah, it does imply that, yes. Because, you know, in finite time, I mean, all the derivatives are going to blow up. Yeah.
Is it phi or blah blah phi?
Yeah, it's phi. This is a definition of a barrier. Yeah.
And we have such a function for all convex bodies.
Very good. We're going to talk about that. The answer is yes. The answer is yes, and right. So this definition, maybe I should have said that this definition of self-concordance goes back to Nesterov and Nemirovsky. In 94. Okay, it's a very beautiful topic, which I'm not going to explain too much about. Okay, so now the sampling scheme. So idea. P of x could be uniform on the Deccan ellipse at x. Okay, I claim that this will have exactly the covariance that you want. It's really, really nice. Why is it? So how do I sample uniformly from an ellipse? I can just take, you know, if I have an ellipse, which is like maybe x times sigma x less than 1, then sigma minus 1 minus 1/2 u with u. Maybe I want to be on the boundary of the ellipse. Uniform on the boundary. That will be a bit nicer. With u uniform from the sphere, n minus 1 dimensional. And let me get my normalization correct. This is correct. Is uniform on boundary. Okay, so I just take a random direction and I just rescale by the appropriate covariance, right? I mean, just if I take x, which is this, then certainly x transpose sigma x is less than 1, right? If this is x, then x transpose sigma x, this is u transpose u, which is less than 1 because u is on the sphere. Okay, so that's the way to sample uniformly from the boundary of an ellipse. Okay, so what does it mean? It means that if I take x, so if I take x plus, okay, so my ellipse here is given by the Hessian of phi. So x plus the inverse Hessian of phi at x to the minus 1/2, to the 1/2, applied to U. This is distributed from Px. Right? This is what I just said. The Deccan ellipse, the covariance is given by the, not the covariance, is defined by the quadratic form associated to the Hessian of phi. So if I want to sample uniformly on the boundary, I'm going to take x plus something which has 0 mean, and which is the quadratic form to the minus 1/2 applied to a uniform point on the sphere. Good? We're good with this box? So now I can look at what is the covariance. So what is the covariance? The covariance at x, it's the expectation of x minus x transpose when x is sampled from P of x. So the little x, they cancel. I get the expectation of the Hessian phi at x to the minus 1/2 times U transpose Hessian phi at x to the minus 1/2. Okay? And what is the expectation of U transpose when U is on the sphere? Okay, so it's rotationally invariant, so it should be some multiple of the identity. And what is the multiple? Well, it's given by the variance of any coordinate, which is 1/n. Okay? So you get that this thing is 1/n times the identity. Now you have Hessian minus 1/2 times Hessian minus 1/2, so you get 1/n times the Hessian of phi at x inverse, which is exactly what you wanted, right? Sigma t now, or sigma t, yeah, inverse is exactly the Hessian of phi. So the Hessian of phi times the Hessian of phi inverse, they cancel each other. And I get a factor n because I have a 1/n here, and I get another factor n because the trace of the identity is n. Okay, so conclusion. V for AHR, okay, the Abernethy-Hazan-Rakhlin sampling scheme, is bounded by n squared. Okay, so this gives you n square root t times range bound. Is there any question on this? So I'm going to say a few more words about the range. But did that make sense so far?
You said before that taking just a small sphere around the point is not good in high dimensions. Can you please describe the difference between this ellipse taking and...
Of course. So what happens is, imagine I have something like this. Then the point is a small ball, it will be constrained like okay, maybe this is not, yeah, I mean it has to really be, okay. You see, yeah, it's like 10-dimensional. So the point is like in all the other dimensions, it can be very fat, the ellipse. Make sense? Like 3-dimensional, just 3 dimension. I have this thing, and then it's going, like that, chook, like it's very long in this 3rd dimension. So this ellipse is going to be very fat in this long dimension, and tiny in that one. Maybe, sorry, here in the, if you have a box like this, and if you're here. If you want a small ball, it's going to be like this. But if you allow an ellipse, I can be like that. Sorry, you don't need to think about 3 dimensions. Just 2 dimensions is fine. Okay, so you use that. You have this long dimension where you can be, you have a lot of space. You're using space much better. Now, of course, this is not optimal. Okay, this is suboptimal because even if you see in this case, like when I get here, I will be very constrained. But I have a ton of space here. So what I can do is that instead of being uniform on the ball, I can tilt the distribution. I can put more mass here and a bit less mass over here, but go further. I will explain that next hour because it's really nice. So maybe I will say less about adaptivity, but I will explain to you how to tilt this distribution to use space in a much better way. And we will basically remove this 1/n factor, 1/n of the dimension. Let me just say a word before the break about the range. So here is a theorem by Nesterov and Nemirovsky. For any convex body, there exists a self-concordant barrier. Okay, so which verifies this thing, that the Hessian is well conditioned on a Deccan ellipse. For any convex body, there exists a self-concordant barrier with range, which is bounded by n times log. So the range is bounded by n times log of distance of y to the boundary. And this log of distance of y to the boundary is exactly the same log as what we got yesterday with the log barrier for multi-arm bandit, and we got a log t out of it. Okay, this is exactly the same reason. So again, you play the same trick that when you in your regret, instead of comparing to the actual opt, you compare to an opt which is a little bit inside, at distance 1/poly t from the boundary. So from this, we get that Abernethy-Hazan-Rakhlin, the regret is bounded by n to the 3/2 square root t log t. Okay. Remember, for multi-arm bandit, we got square root nt. Okay, so there are 2 more square root n now. So after the break, I will tell you n square root t log t by describing something better than this very general theorem by giving you an actual very simple function which is a Kramer transform of the uniform distribution on a convex body, which we call the entropic barrier. And I will just do the basic calculations of it. I think it's quite nice. And then I will tell you about adaptivity. Any question before we go to the break?
Does it make sense to use like the John ellipsoid?
No, it does. So it makes sense. Problem is the John ellipse does not, you cannot find a phi that gives you this as the Hessian, but yes. There is much more to say about this comment. There is a lot to say about this. So maybe I take it offline. Yeah. Short answer is yes, you can do that. But then it doesn't exactly fit this. Okay? Thanks.
Thank you.